why don't we talk about what we might do if it were the case that we needed to describe something about this distribution, but those 4 singular scalar values, our mean, standard deviation, or mean, variance, skew, and kurtosis, were not sufficient. And so, in our next question, just tell me what it looks like, okay? We're going to talk about common graphical descriptions of these data sets. If we take our data set, we talked about how we might look at this in terms of the histogram of values. And so here is our data set, and you can see our histogram of the values and the frequency with which the values appear, or at least the number of times the values that appear. So you can see these values bucketed around 20-ish to 30-ish appeared about 1,400 times in our data set. And this might be a reasonable way for us to graph this because it gives us a little bit of a sense for where the values are clumped, and we can begin to see maybe a little bit of a shape of this data. But more formally, one thing that we might want to visualize for this data set is what we call a probability mass function. The probability mass function is saying, instead of giving me those values in that fashion, tell me what the probability, tell me what the frequency in very broad senses, tell me what the frequency of each value is. And so if we take this data set and we compute what the unique values are and the number of times each unique value appears, and we plot that, we get the probability mass function. And it's called a probability mass function, but it really is more of a notion of some sort of graph here, at least for our purposes. Now, when we do this for this data set, we might not get something that we really like to see. Here, what we can see is, well, I should take a step back and I should say, we'll talk in a moment about the difference between a continuous and a discrete distribution. But here we can think, if these values were from a continuous distribution, if they could have been any possible real number, then the probability of any one real number, the probability of looking at your watch and seeing all the way out to the picoseconds and that exact value is going to be very, very, very low because there's an infinite number of possibilities that you can see. It's continuous. But if you talk about something that's a discrete distribution, this probability mass function is actually very valuable. And so one of the little pieces of sleight of hand for this particular data set is this data set is much more likely to be a discrete distribution, because if I have a continuous distribution here, you can see that's a really bad probability mass function. This doesn't tell me anything, because the probability of any individual value is just the total 1 over the total number of values that we saw. So this is really only meaningful if we're talking about a discrete distribution. We're only talking about values that have a discrete number of possibilities. And then we get a little bit of a shape here, and we can see, oh, the discrete value around 20-something occurred maybe 5% of the time. Much more directly useful than a probability mass function is a probability density function. But this is a little bit hard for us to compute. The probability density function is our way to graph what is the probability of being around, not being exactly that value, but being around or near that value. And so I have to reach for scipy.stats in order to be able to compute this. Here is a probability density function for this particular data set. And so this isn't what's the probability of having an exact value. This is what's the probability of being near that value. So what's the probability of being near 21? And you can think, well, that's a little bit more meaningful for a continuous distribution because we're not saying what's the probability of being exactly 10.05 and 3 picoseconds. We're saying what's the probability of 10.05 or being around it. This requires us to use a little bit more mathematics in order to actually compute. So I don't want to go into the mechanics of computing it because I want to show you something related to the probability density function that comes up a lot, and it comes up a lot in my work. The cumulative density function, which ends up being very easy for us to compute for both discrete and continuous distributions and is incredibly useful as a way to describe a data set visually. The cumulative distribution function is, at any given point on this graph, what is the probability, or what was the frequency? And we're using probability and frequency interchangeably as a simplification. But what is the probability or the frequency that you are less than this value? And so if we take our data set, and if we take our data set and we compute the unique values of this data set, and we plot the cumulative sum of all the values that were under a certain point. So you can see here, this is the cumulative value, or the cumulative percentage of all the values that were under this point, under 20. This is what the cumulative distribution function gives us. And you can see we can actually look at it for our real data. We can do this directly in Matplotlib with a cumulative, with a histogram. And so here you can see we have something interesting. This tells us something about the data. It tells us something very powerful about the data. Note, the cumulative distribution always starts at 0 at one end and always ends at 1 at the other end. Because 100% of the values, you have to have seen 100% of the values at some point, and at the very beginning you've seen none of the values. What's interesting about the cumulative distribution function is what the shape of that curve looks like, and where that curve is located and how steep that curve is. Because this tells us something really interesting about this data. What it tells us is, at some particular point, for example, if we take a look at this point here, 95% of the values occurred before this point. So 95% of the values were less than 42-ish. That's a really interesting thing for us to say. And it tells us something about how these values were distributed. Are there lots of outliers, and this thing is slowly climbing up, or does it climb up really fast and then head off? Because the values are clustered in a particular fashion and distributed in a particular fashion. I end up looking at cumulative distribution functions and plotting these for people almost as frequently as I plot the actual data, because this can give us such an interesting view of where the data is actually located. And one of the little sleights of hand that I showed you here is I computed a percentile. When you take a look at the cumulative distribution function, you get a notion immediately of what those percentiles are. In other words, your P95, P99, what is the probability, or what is the value under which 95% of what we saw appeared, under which 99% of what we saw appeared? And it's a very nice way for us to describe something about a data set, both visually and in a particular singular scalar value. 99% of the data appeared at this point. 1% of the data was above this point. 95% of the data appeared below this point. 5% of the data appeared above this point. Or similarly, we can compute this in terms of quantiles, where at least in NumPy terms, quantile and percentile are basically the same thing as just whether you give a value between 0 and 100 or 0 and 1. And we can even relate this to previous formulations like our median, our 50th quantile, or our 50th quantile is basically our median. And so what we're looking at is trying to get a sense for where are most of the values located, and that's what the cumulative distribution function gives us, and it is incredibly useful for that purpose.